Bruno did this already. My name is Mischa. I'm a data engineer at Vue. So quick overview of the whole presentation. I will first give you quite a detailed background because I think then one understands the project better, what it is supposed to solve. And I'm afraid we will have to go into some aspects of Kafka quite detailed because we use Kafka a lot also to solve this particular problem. Then we will go eventually into the design and then what we have done in Clojure. But be patient, Clojure will come, but quite late. And finally, there will be a demo if time will be enough. And I also try to show how we were testing it on CI. Okay, so the usual disclaimers, I explained it before already. A lot of the design was done already before I joined the company. And I'm not a Clojure expert, so don't expect any new cool things. I'm just learning myself, started last May with Clojure, and I'm not even a Kafka expert. So now let us start. So what actually are we doing at Vue? So let me explain this as well. It is about advertising, and it is a special kind of advertising. It is out of home. So while it is not online, there's still a huge amount of IT infra behind this. For example, you see here, there's a player behind, or possibly there are even two players behind that screen. So somebody has to organize that the videos, creatives code, will be uploaded, distributed to all the players in the world. You can imagine how many we have. And these players will send periodically so-called proofs of plays, or POPs called, back to the media owner, for example, for billing purposes. Now imagine you are a media owner who has, I don't know, thousands or 100,000 of these players, and the players sends them back every 2 minutes, something like this. I don't know exactly the details, how much data that is. I think this goes easily into billions per week or possibly billions per day, and they are also needed for billing purposes or other things. Now, this bus shelter here is from JCDecaux. That is, I understand, possibly one of the biggest or the biggest media owner in the out-of-home space. I think they are active in about 80 countries. They have show advertising in many prominent locations like here, that is Oxford Street in London, obviously, but also airports, Heathrow, you name it, worldwide, Hong Kong, train stations, in department stores. And once you know the name, you see it everywhere. So at one point, they decided to move out part of their IT into a spin-off to offer their infrastructure also to competitor. And this is how Vue came into world. So we are a spin-off of JCDecaux, founded 2018, and the name stands for Viewable Impressions Out of Home. Impressions in advertising is the business, the currency, that is the money. So now what we are trying to do, or what we are actually doing, we are a global digitally out-of-home marketplace. And essentially that means we connect buyers and owners, so media buyers and media owners, and there's also an exchange part of it. And sometimes I feel quite often that I work for a financial organization where I've worked before in finance, investment banking. A lot of the terminology is the same. So now, what does it mean for our IT? So let's assume this is an extremely simplified view of JCDecaux. All of these little things mean some apps. Obviously, they will also talk to each other. But a lot of the stuff is backed by Kafka. So a lot of things go to Kafka and then to other apps. We have a lot of different data types. And once Vue was spin off, of course, some of the apps moved to us, but also the data, but there needed to be a lot of shared data. So the first approach was the so-called Kafka mirror. As far as I know, I think it's an open source project. It just mirrors configuration-driven some topics from the source cluster to the target cluster. However, it still doesn't feel right that so detailed two separated companies have this kind of shared infrastructure. So in the long term, this is currently not fulfilled. This mirror, I guess, will be removed, and we will go to a really nice demarcation border between the two companies. There will be HTTP gateways where the data is pushed in this direction and also in this direction. Now, the talk will be exactly about this area here. So we have data, and it doesn't matter where the data comes from. Originally, it may even come from JCDecaux, but we want to push it back. So as it turns out, JCDecaux is not one unit, it is many units distributed all over the world. And as it also turns out, we want to push data not only to JCDecaux, but as I've mentioned before, we want to serve other companies as well. And these might be major owners. So people who have these screens like the bus shelter or at airports, but also media buyers. These are then big companies who want to buy advertising, or the agencies in between. Okay. So this is where somebody has designed, before I joined the company, a webhook system. So the idea was, we push the data out of view, whatever data this is, these different data sets, via a well-defined contract to all these different subscribers. So that means a subscriber can subscribe to a certain event type, what was previously defined as a data type. It maps usually to a Kafka topic, but the subscriber wouldn't know this. This is an internal detail from us. They also have an optional filter. They are not necessarily interested in all the data, and they just have to give us a target endpoint where we will send the data. Obviously, there will be some access control behind. Not everybody can see everything. So I thought, let's quickly design this together. I haven't mentioned what the subscriber has to implement is the so-called events API. That is just a little Swagger thing. We will go later into the details for that. Okay, this is quite, yeah, I have mentioned that already. So let us quickly design this a bit. So here, this is the worker, first version. It's a simple thing, runs in one JVM, so one open operating system process. It consumes from Kafka and pushes the data to the subscriber. So the events API is, I'm not sure if that's the latest version, but conceptually that is. There's a validate endpoint and upload events endpoint. All goes via REST. It is JSON what we send, but usually here inside we have Avro. So it runs on Kubernetes, but still this wouldn't scale at all. We expect hundreds of subscriptions, and possibly a company will even subscribe to the same subject twice because they have different IT departments who have different requirements, and they also don't need to couple these requirements across the different teams. So definitely this will not scale. By the way, this is how the payload looks like. Very simple. The body has an array of envelopes. It's just some wrapper stuff. And the value is in any, and in the header, we only assume the market because this is the only thing the subscribers can currently filter against. So the next level of scale, we put in this worker, still this little yellow box. We do a little bit of threading. So we have a couple of more processes. We can cater for more subscriber, but this still doesn't scale at all. And there's also no robustness built in. If this worker crashes, what are we going to do? So let's have the next version of it. And here we go. Now we have a group of workers. Let's call it a cluster. They all work together. And they have the job to push the data. And we have the job to organize this cluster. So distribute the work, distribute the load across these different workers. And if one worker crashes, obviously we have to reorganize, redistribute the work. So this looks more stable. That seems to be horizontally scalable on two levels inside a worker, and we have a cluster where we can start additional workers. So what do we need else? We offer in addition, this is a different process, visible here from the outside world, a subscription API. This has some crude operations where the subscribers can create their subscription, suspend it for a while when their IT system is down or they want to upgrade, resume then, amend this if they have some changes, or even delete it if they don't need it anymore. And eventually, so this is public, they will be aware of this, they know this is their way how to create subscription. It's not necessarily a human. A lot of these subscriptions will be automatically generated from the companies in case of interest. Finally, during the work, this was not initially planned. We realized we will need an internal additional admin API so that we can fine tune, customize some of these subscriptions. Some of these subscriptions might have a higher load, and we have to fine tune them with some Kafka knowledge, which we certainly don't want to give the outside world to the clients. So a quick look how a subscription looks like. Essentially, this is a top level overview. It has a source part where the subscriber just defines what is it actually the event type, which under the hood maps to a Kafka topic, and the target, which is a bit of authentication. We offer several things, basic, JWT, API key, stuff like this. They can fiddle around a bit with the format, if it's gzipped or not. We may or may not offer in the future Avro, not sure about this. And certainly the most important thing is the endpoint. But the format of the message itself was defined before. Now, I mentioned the event type maps to a topic, and obviously not everything is in Kafka, but we said if somebody needs data, we have the data. Is it only in a database, but not in Kafka? But an external subscriber will need this. Well, then the job is we will put it into Kafka. So Kafka will be the only source for us to push the data outside. If a new system comes, has external subscribers, okay, they will need to publish also to Kafka. Now, the subscription view is only the external view. We have an internal view. This is the task. These little blue boxes here should present them. This has much more knowledge. So a task is executed in this single thread, essentially how we have seen it before. It consumes, it pushes. It has much more fine granular configuration. We can scale also tasks. Some topics have high volumes. We can give this particular topic subscription more tasks, and therefore the relationship between the two is not one-to-one. The subscription can lead to many tasks, for example, for high value, high volume Kafka topics. Now, here we go. How do we design this? This was our next question, not solved by me, decided already before I joined. It was decided to do this as a distributed task execution system, where actually a lot of the work is independent from what we really do in an individual task. Our individual task is consuming and then uploading. But the main problem is how do we ensure that it is scalable, that it is robust? So let me put here some further definition. What is a task in this context? It is something long running and also quite important. It is restartable. That means if the worker where the task lives on crashes for some reason, we can put the task somewhere else and it knows exactly where to start. We don't want to have any data lost. By the way, we don't guarantee once and only once delivery, but we still at least guarantee we deliver the messages. And obviously there are the further non-functional requirements that is quite clear. Okay, so how do we build this? So now I'm afraid before we go there into details, we will have to do Kafka in 5 minutes. So now don't get excited. I can't explain Kafka in 5 minutes. It's not possible. We will only discuss here what is essentially needed to solve this problem, only with my little knowledge. And I still think it is quite interesting, and it is not the normal standard Kafka usage here. So let us start with some basic terms. So the most basic term is a broker. In the backend, a Kafka cluster just consists of a lot of brokers. They work with each other, they share the load. On these brokers, we have topics, and obviously we have some external processes who want to consume, read from a topic, and this is the consumer. It will get more complicated. This is just the start. So the next thing is what we have is offsets. So a consumer is always at a certain position. Once the message is read, or the messages, individual poll can include many messages, the consumer will commit, and then the consumer is on somewhere else. Each individual consumer has their own offset, so it acts like a cursor. So the whole thing is Kafka is not only a message system. Think of it as a mixture of a database where you have cursors and the retention and the message system. That is actually the best view of it. And then we have also producer, but I have to tell you, producers are completely unimportant, like the broker itself. So these two concepts will disappear now. Now, a topic can be divided into partition. The reason is partition can be distributed on different brokers. They might run on different nodes. So the data can be distributed. However, for the poor reader, now the job is double. Has to read from this partition and that partition. It might be even 10 or 12 partitions. So therefore, there's a new concept, which is the consumer group. That means consumers can organize themselves to be in a group. You can still have others group as well. The group is aware of each other's consumer, and they do the processing of the message of the given topic in an orchestrated way. That means, for instance, this consumer might deal only with partition 1 and that consumer with partition 2. The consumers inside a group, let's call them members, they can live on the same JVM or whatever programming language you use, or on a different node. It doesn't really matter. Once they start, they will be made aware of each other. You can add another consumer, and in this case, this guy will be idle because there are only 2 partitions. So if you add more consumers than partitions you have, nothing will happen. However, if one of the consumer crashes, the work will be reorganized. So let's look at this reorganization in more detail, because this is quite crucial for our solution. So here we go. We have now here 2 topics, A and B. They are distributed into many brokers. We don't see here the concept of broker. It doesn't really matter. And in real life, by the way, a topic is also replicated. And also this is not so relevant. We don't see this. And here we have 2 consumer groups, the yellow one and the green one, and they happily consume. It's nicely, not really nicely balanced. This guy has more to do than this guy. But what can you do? You have only 3 consumers, but 4 partitions. Next thing, what happens is this guy crashes. So you don't want to lose the data here. So something needs to happen. And what happens? That is called the rebalance. So previously, GC1, this guy had only 1, but after the rebalancing, our crashed consumer has disappeared, and this partition is reassigned there. Now, the next thing, which may or may not happen, another partition appears. This doesn't happen too often, but it's still possible. You can always increase the number of the partition. Why not? If you have realized that you have more data than expected, and again, the same thing needs to happen. We will need to rebalance, and the new partition need to be covered by this particular consumer group, because you want to consume the whole topic. So let's now have, as a last thing, the consumer comes back, and boing, the consumer gets a partition back, the crashed one. It doesn't need to be necessarily the same. It will be the partition which the rebalancing algorithm has decided before. So how does this work? That is the crucial thing here. And there is a rebalance protocol. Let's go to details. So a lot of distributed systems obviously will have the same problem, and they will have solved it in their own way. What do we have, for instance? Cassandra, distributed database, Elasticsearch, or any distributed caches. In order to organize robustness, they will have solved this. Okay, so first of all, let me see what I have meant here. Okay, yes. The first thing is, when the rebalance protocol actions, it needs to have some knowledge of the group. So we have membership organized by heartbeats. The next thing is, we need to discover new work. So this was the example when we had the new partition. So that is new work, which needs to be distributed. So the rebalance is triggered either by a membership change, a new member or member lost, or by new work or less work. The next thing which happens usually is leadership elections. I mean, we know all of this. This is the bread and butter of distributed computer. So also in the group protocol, it happens. If in this group something happens, either of these things, Kafka will select one of the consumers as a leader, and the leader will create new assignments. And finally, the members will get their assignments. The assignments in this case is a partition or many partitions, and they will execute the partition. So this whole thing is very important for our solution. Just here, some information. This talk by Gwen Shapira is really good, really beautiful. She explains it all. She's from Confluent, and I learned a lot by just checking this. So now on YouTube, so just Google this in case you are interested. Now look at this. We will keep here the same picture more or less, but we will change the titles of the picture. It is not anymore, one moment, I have this stupid Zoom thing in front of me. It's not anymore partitions, but we have tasks here. And it's not anymore the consumers, but we have workers here. But it is essentially the same thing. I mean, I've done it slightly different. The group is now all of these workers. So we have a group of 5 workers. But we have, in this case, let's assume 2 subscriptions. One led into the green A task here, and the other led into the blue B task. And still the work needs to be distributed. So the task needs to be distributed. So let's do the same. Oops, what happened here? Sorry, the same thing again. So we came from here, a worker dies, the task needs to be redistributed. The tasks were scaled up. We can do this when we see it is too slow. So a new task here needs to be redistributed. This came from here, even though it looks ugly. I couldn't make it from here because the distribution should be still nicely well distributed. So we want to have 2 things essentially, that as few as little tasks are reassigned without need. They should stay where they are if possible, point 1. And point 2, we want to have the work as much as possible equally distributed. So this guy shouldn't get 3 and this one only 1. And now let's have our crashed worker back. Here it is. And it gets also the partition back, or another partition. And again, this is all nicely distributed. Now, the most important question here for this project. Can we reuse Kafka's rebalance protocol for our own purposes? And the answer is, I mean, you guess it, obviously. The answer is yes. We can distribute it. We can reuse it. And actually, it is already reused inside Kafka as well. From the Confluent platform. They use it inside Kafka Connect. So they have refactored some code already. It still lives in an internal packages, and it is not documented. Trust me, it's not documented, not at all. But if you watch Gwen Shapira's talk, they are actually interested to put this into their public API, and they are interested to get our feedback. So it will be at one point hopefully documented, and it will be at one point moved out of the internal packages. So a quick overview again before we continue. So the team here, just to see how parallel this is. For the consume, the team is a consumer. Here it is the worker group, the cluster. A member is an individual consumer, and here it's an individual worker. And the universe of work, all partitions for the Kafka consume, and all tasks for our distributed task system. So now let's go quickly again through the individual steps. And I will do this quite often because it is quite important. So the first thing is we have a change of something. Something has changed, we need to react. Either a member died or new member or work has changed. Whatever the work is, it applies for no. The next thing is mentioned, leader election. Next thing, and now we talk about how it is actually implemented by Kafka. So Kafka will decide one of these members in the group will be the leader, and Kafka will also request from each of the member, give me your current state. What are you doing currently? For instance, in the case of consume, which partitions are you actually doing? The reason for that is they don't want to move the partition processing randomly. They want to leave the partition as much as possible where they are, and we want to do the same with the task. A member can also give further information, which the normal consumer doesn't use. It can actually say, look, I run on a huge box. I have an enormous amount of memory. Give me more tasks. Kafka doesn't care. They just want, we will later see this in details, give me all your metadata. And as soon as you use the rebalance protocol for your own purposes, you define what your metadata is. So this I mentioned here. The member return their state, and we can put there anything we want, depending on your application of it. Finally, the leader creates the new assignment, and the input for that is the member data of all the metadata of all the members and the reference to all the units. That means the leader needs to know about all partitions or all tasks, depending on the use case. Finally, or not finally, let's see, the assignment is sent by Kafka to all of these members, and the members, so the individual consumers or task executors, workers, they are responsible to implement or to execute the assignment. So what will we need to do when we use this protocol for our own purposes, and what is Kafka doing for us? Let us go through this. So first of all, if we are an own worker, we need to join the cluster, and we need to trigger the heartbeat so that the other group members are aware of this. We also need to do on our own. Kafka, the protocol is quite stateless. It's quite clever, and it doesn't assume so much. You need to keep track of your own work. In our case, you need to know the whole universe of the task. The next thing we need to do, look here, is quite late. The steps in between are organized by Kafka themselves. Each individual member, so in our case, each worker, they need to know their state and they need to return it back. Now, while Kafka decides who the leader is, it is left to us to implement the assignments. So to implement the rebalance. Because the protocol, the rebalance protocol, has no idea what we are going to do. So it's left for us. And it is implemented for the Kafka consumers, and we had to implement this for ourselves. And the final thing is here, again, 6 is organized by Kafka, and 7 is the next thing we will have to do. So still, we haven't heard anything about Clojure. I'm sorry, but we are getting closer and closer and closer, but not yet. So don't get afraid of the next diagram. I know it looks horrible. It looks a lot of UML, Java thing. It's not exactly UML, it's a sort of mixture, but I found it quite useful to get an overview how we have implemented that. So let me go through this quite detailed. So the top layer here, the yellow, light yellow layer, is what comes from Kafka. These are Kafka classes. The main thing here is the abstract coordinator. And in order to use this, I have decided to build a little bit in Java itself, which is this layer here, before we go to the blue or dark blue layer, which is the Clojure world. So I explain why I did this. It was a bit controversial, I admit this. People were wondering why I don't implement this guy directly in Clojure. Well, for me, the reason was quite simple. What is your guess? This class has about 1,600 lines when I looked this morning. It's a monster. It is too big. I mean, this is the file. In the file are several classes, but the class itself. I don't know how many methods it has, but conceptually, we need very, very little. If we go back, we need essentially 1, 2, 3 things to implement. So I decided to separate the things we need to implement into a leader functionality, which is create the assignments, into a member functionality, which essentially is return the metadata and implement the assignment. So let's go through this. Another information, this is all Kafka. And we see here also, I think nicely, the 3 different ways we use Kafka. It's still the same cluster, definitely, yeah? But this Kafka is just our way to deal with the group rebalancing protocol, so not the normal vanilla consume produce. This Kafka thing is where the real data is, which an individual task executor will use to consume and then push to the subscriber. And we use Kafka also. Remember, we had a subscription API. The subscription API will push the subscription in here, and the worker will read it from there and convert it into tasks. So we have 3 different applications, very different meanings of Kafka, but it is the same Kafka protocol, Kafka cluster. Okay, so off we go. First step here, inside our thing, we have to kick off the group. I show you how it looks like. In my little Java thing, we have just to call from this abstract coordinator, ensure this and heartbeat, and off we go. That's it. So, oops. The next thing is we have a change, a rebalance trigger. So either the group protocol said, look, there is something happened. Somebody has crashed or somebody is new, or we have a new subscription. What happens there? Oops. I'm a bit confused here. I guess something went, yeah, maybe I don't have any further details here. Step number 3 is we asked for the metadata. In the abstract coordinator, it looks like this. In my stuff, I separate this out. It is just the metadata now. And finally, in Clojure, it is the implementation of the interface. It is done via Refi. And it is just this little method here. So remember that the member has to implement 2 methods. And there isn't really much. It gives back some runtime info, which is the memory, CPU, and all the stuff. And it knows which tasks are doing it has. We will look later into detail what it is. So what is the next step? The next step is here, number 4. So I just described the steps we have to do. Number 4 is after the Kafka protocol is discovered, it has collected all the metadata. Now it is given to the leader. The leader is usually, in my experience, the same. It doesn't need to be the same. We don't implement against this, but as long as the node doesn't crash, it will be always the same leader, and the thing is always called in the same thread. So that means all different events are actually put into a sequence. So how does this look like? Again, we have to return just some bytes, and we get some Kafka classes here as an input, not so interesting maybe. The little wrapper I wrote just makes a map out of this, also not so interesting. And finally here is the Clojure code. This doesn't do the rebalance. This was actually one of the more complex part of it. We don't see all here, but what we do is actually, well, I don't think it's worthwhile to go into this, but we trigger here in Clojure the build of the reassignment. So the next thing is, finally, Kafka has received all the reassignment. It distributes them to all the members. Our members are here, in this case, the scheduler. So how does this look like? The member, so to speak, is a bit funny. One needs to learn or the meaning behind their methods. It feels like as if they leave the cluster and join again. Therefore, it is on join complete. And now we talk about the set assignment thing. And this, I thought we go into more into details. That is the second one here. Let me move this thing. So we have to have some state here. The state is here in this atom. So it keeps all tasks. The key of this is a map. The key are the task itself. The values are stop functions. So it gets the individual assignment for this one. It has to update the schedule. I think I have the method here as well. So it's just a quick run through, not too detailed. So once the schedule is there done, we will have to stop many tasks potentially, and we have start them as well. And finally, he's also the start. Again, it needs to populate then this atom here, the task to stop function. There is somewhere also a factory involved. This is the worker function, because it comes from outside how we create something. There's still some generic part here. I will explain this later. And finally here, the thread is started. The factory creates the new task, and it puts a predicate into the new worker, and the predicate is just the front end. We see this here of the atom, because I don't like passing atoms all over the place. Then in my experience, people just start to mutate them, and now they just have a Boolean predicate. So, okay. So I didn't mention before, there's a 6 as well, but this thing here, the orange part, is completely reusable. Finally, Vue is not only a Clojure shop, we have also Java projects. So it's quite abstract. There's no hard coding what a task really is. And even this light blue word in Clojure is pretty abstract. It might be a bit over-engineered for some people, but for me, it's easier to think the different concerns. We talked about this before, what they need to be do, and then the namespaces get very small, and this is how I like it, how I can think. I can't deal with these big monster classes, 1,500 lines, or big namespaces. Okay, finally, we are here at 6. A task was created by the factory, called differently in the code, or a task has disappeared. So the task is now starting. Let's have a quick look into that, how this looks like. I've called this slide "A task never fails." I will explain it in detail, and obviously Bruno will know what about that is. It is his famous safely. If you haven't used it before, I can only suggest do it. It's a very nice circuit breaker. So what it means, what has a task to do? That is a single task against the subscription. It will constantly poll from a given topic. It will do a little bit of filtering and then upload the data if there's something. Now, both of the stuff can fail. More likely this will fail. Either the subscriber is down, or the password is wrong, or it was incorrectly configured. But we don't regard it as a failure. The circuit breaker will do it again and again and again and again until this task is canceled, the worker has crashed, or the subscription was suspended. So there is this Boolean predicate, which I showed before, inside this safely in order to gracefully stop it. And task never fails mean it doesn't fail. It might not progress. But remember, we have the offsets. Once the worker crashes, and the task is distributed to a different worker and it starts to live again, it will know where it continues. So now here is the code of this particular poll. As I've mentioned before, there's an atom here. Also, the send function is not inside here. The filter function is also not inside here, so you can more easily test this, inject any kind of mock you want. This code is pretty much how Kafka consume with the library Jackdaw. I haven't mentioned that. That's a wrapper around Kafka. Kafka's, of course, offered to us as a lot of a Java library. So usually here is the while scheduled. When this goes wrong, the whole safely will stop as well. But otherwise, it will endlessly continue here, and it will do poll a little bit, filter, and once we have found some record, it will send it. It looked nice, simple, but guess what? In this simple code, two really major bugs. I mean, you won't see the bugs anymore, but I can still explain them. They were found, but they were found only on CI. The stuff was already for weeks in dev, it was for weeks in UAT, and obviously also on our local boxes, but it never happened, the error situation. And why? Because we never had a lot of stuff happening at the same time, which you usually don't do. So the bugs were only found on CI, and here we go. What were the bugs? The commit sync. So I told you before, you need to tell, once you are done with your work, that the offsets can be moved. But what I, stupid me, as a beginner in Kafka didn't know, the default for the Kafka consumer is auto-commit. So I didn't know that I have auto-commit configured, not actively, but this was the default, and it didn't fail when I manually committed. I think most databases will actually fail if they are on auto-commit and you manually commit. However, this happened only, you saw the issue when during a lot of data coming, the task was stopped. It needed to move to another thing, to another worker, but it actually thought it is already committed. So I can start to process the next messages, and we had data loss. So where was the other error? And Bruno will laugh certainly about this. Again, me, the beginner, I didn't know that the circuit breaker name needs to be unique. And the reason for that is there are some resources behind. So this doesn't lead into data loss, but it leads into quite considerably wait until the resources are available again. Same circuit breaker name means the resources are shared. Usually this isn't a problem because you have only one consumer for a certain use case, but we have here a dynamic number of consumers. Okay, so how are we doing time-wise? Okay, I think I need to get faster. Okay, so before we go to a demo, a quick overview about our dev stack. So it's mainly Clojure, just bits of Java. We use Composure, and our endpoints are usually Swagger described. We use Plomatic schema. I'm a big fan of schema, doesn't matter which one. Kafka is wrapped via Jackdaw, and then some other things. Yeah, it is quite standard. So let's not go into details with that. And now finally, demo time. Okay, oops. So let me hide this quickly and see where we are. Okay, I have a REPL started here already. And let me go first somewhere else. So let me show what the normal developer does here. Okay, that. Okay. Sorry about this. Oops. Oh gosh. Okay. So as we I should have prepared this better. We definitely need Kafka running, and Kafka comes with some couple of other services as well. We use schema registry. The reason is the data is AVO described, so it is typed, so to speak. And there's also zookeeper needed. So the normal developer just needs this running on the box, and we will need to have this running also later for the tests. And finally, this is the repo of the worker. We need to have also, let me put this somewhere else and close this on. So we need to have the subscription API. It's a different repo, a different microservice. So we have it here as a Docker image. So a quick thing though, before, oops, that is the wrong one. Still one diagram, sorry about this. I hope that's the last one. So this is another big overview. We have the subscription API, blah, blah, blah. Here's a worker in details. I just wanted to say here, we need to have for the testing work subscribers. So we need to have something locally and ideally for each of the different use cases we have. And therefore we have a little test harness back here, and I will start this here in the REPL, start this thing here. Sorry, let me. Okay, so, and I will explain what it is. This will be this UI. It runs on 3030. So here we have local test endpoints which mimic the subscribers. We have here 7 nice subscribers named after some random names. The endpoints exactly fulfill the Swagger contract we have defined. And this is very much a subscription which we will have to create. So let's see what we can do. So this is some test event. It looks really stupid. And we can send it. I will intentionally use here the wrong event type because subscriber Anna, as described here, accepts only assets. Let me execute this. And so we will have 2 errors here. We don't want to get pops and we don't want to get these kinds of markets. Let me just quickly fix this. And then I explain why this is useful to know. So it doesn't want to have market string. It wants to have, for instance, this market. And now we may or may not get a 200. We get a 200, but let me execute this more often. You see, a couple of times there are random errors. So we have now these tons of test endpoints. They behave usually quite nicely. They have a random factor of 25 of the requests will fail. And we can also check what they have received. So let me show what I mean by this. I just executed. So we executed, I think, 11 requests. The random errors are 500s and the safely will retry. So I don't care about this. But we had in the beginning one with the wrong market and the wrong asset type. So why do we have this? Not only for the development, our CI test will actually go against these different endpoints, each of them having an own subscription created during the CI test. And at the end, or a couple of times also in the middle, we ask the control endpoint, how many have you received? And ideally, we don't want any 400s. And at runtime, FAIR will create random errors, which will create random 500s, but we will still want to have, in the end, the right number here. Okay, so this is all. So now let's look into our next API. This is the subscription API. This is a real thing. FAIR, by the way, stands for Test Harness Event API. This is the real thing, the subscription API. Where the clients can create their subscription. We have already 8 subscription, I hope, or 7, I'm not sure how many we have. It looks like this. This is Anna. Let me copy also the subscription API. It's essentially what we have seen before. Event type, blah, blah, blah. and some configuration. This has three tasks. So one subscription will create 3 tasks, and we can even fine tune this on Kafka. So there are a lot of endpoints here, no point to go through all of them. And finally, we have the worker here. This one will fail now, right? We don't have a worker started. So let's start a worker. Should start an individual worker. By the way, notice here the color scheme there will log in pink, and the worker will log into different colors. The blue one will be more framework style, and the yellow one is very much webhook specific. Blue one is more task specific. So this side should be available by now. We can do a lot of things. The first thing we shall do is, again, a lot of tasks, endpoints here. This is called tasks by worker. We have only one worker currently. Let's execute this. One worker, my box is called like this, was not my idea. It runs on this funny port. And we have 0 tasks. And oh dear, oh dear, oh dear. This is definitely wrong. Have I forgotten to, okay, here the presentation goes wrong. Let me just check if we really have. Okay, so maybe stuff was balancing. So let's be patient. No. Okay, sorry about this. Don't know what's going wrong, but this is nice. This is what we have with live presentation. Sort of a pity though, because it is not obvious to me what the problem is. Last check I have here. Subscription. Try it out. No, I mean, maybe something went wrong in my setup. We had today some funny issues and I fiddled around with this. However, let's not worry too much about this. We hopefully still will go to the tests. So back to the thing here, what can actually fail? So obviously Kafka can also fail, but Kafka is the fixed thing in our equation. We assume it will not fail. It's not really realistic, everything can fail, but we have not built the thing against a failing Kafka. We have built it against failing workers, temporarily not succeeding task execution, and definitely against failing subscribers. So now let me show you how our test works. So I have here the test plot, and then I will explain how the test works. So the test uses 2 different things. Test containers, a really good open source project, just fantastic. It allows you to programmatically stop and start Docker containers. And as you have seen before, we will need Kafka, Zookeeper, schema registry, and the subscription API running. And the world is asynchronous, so we need some asynchronous testing. And I had a quick journey from Clojure test to Mischa, and finally I ended up with Tested, which supports out of the box async testing without me writing too many funny loops which check the state or something like this. So there is quite a basic setup. We have to kick off all the test containers. We have to create the topics. We have to create the subscription. One of the subscription will get wrong credentials, and one subscriber subscription we will create much later. Then we start the cluster first with 3 workers only. We publish tons of events. We will check some data. I couldn't show you this because the stuff didn't start properly for the first time for a month. That is the way it is with demos. But we will check the offsets so we know that everything was consumed. We will check how many tasks are running. We will check how many messages were filters and how many stuff was message were arrived at the target endpoint. We will publish even more. Then we will stop one worker, again, a lot of assertion. We will fix Marta, we will give her the correct credentials, and then we will have a lot of stuff at the same time. And this is how I find the other bugs. We will add a further subscription. This is a Kafka term. This further subscription will go to earliest. That means it will read everything, even what was published before, subject, of course, to the retention, only the messages which currently exist, which exist even before the start. Usually, the subscriber will get the message only as of start of the subscription, but they can also ask for the existing history. We will reinstate the crashed worker or the stopped worker. We will scale up Paul. Paul stands for POPs, and it will get more tasks, and it will get more events. And again, the assertions. So let me see if this at least works. So this is the Kafka thing. Okay, I'm struggling with this thing. Yeah, go away. So I think I have, wait, where am I here? I think here, yes, here am I. Yeah, I am. So let's do just line test. The test is a bit slower, so we don't need to watch this. Ah, that's the wrong test. We have to do line test E to E. There are some test selectors. That's an end-to-end test. We, of course, have lots of unit tests to cover the individual small functions. But we need also to do it end-to-end. The group protocol is a framework. It's hard to mock. It's not a library where you can mock the other side of it. You are going to be called, and it needs to be the live system running. We see already here a lot of stuff is starting, but now let's have, no worries here, it's just some Docker thing. Let's look here into the test. This is the test, and let's make this more. So I personally found the test got quite readable. So let's try to read, not the beginning. In the beginning, these are just helper function, which we will come. So is this readable size-wise? No, a bit bigger. So we will first define the fair state. Remember the control. We just need to keep all our failures somewhere. And we will start the container. So I give you a quick run through at this as well, because I find it quite interesting. So remember, we had two things we have to start, three things: the Kafka container, the schema registry, and the subscription API. But inside Docker, they live all in the same network. So we have to create a network. By the way, test containers allows also to kick off a Docker compose. So you don't need to create, to start the containers individually. But the Kafka container is here quite convenient. It has zookeeper built in, and I also couldn't make it work right away with the Docker compose working. That's the first remark. The second remark is that there is also a Clojure wrapper to that. But again, I couldn't make it working right away. So then I thought, this is just 60 lines of code. The Clojure, the Java API is nicely done, and it is not necessary to write for everything a wrapper and to have then another, I mean, an external wrapper, an external library, to have another external dependency. So let's see how, for instance, the subscription API is created. First of all, you need to have, of course, the image name that lives, in our case, on ECR. We run on AWS. You give it the network, which comes from the parameter. You can actually say, like in a Docker Compose, it depends on this and that. You can even define an own logger for this. And I have given this own logger even an own color, so that it is quite helpful. You have to tell which exports you expose. And this is a very confusing thing. I will talk about later about this. And you can map some volumes. So the subscription API needs a config file, which is in GitHub. And here's the mapping. The other stuff is the same. Nothing else to be said. However, the thing returns something. And that is a confusing thing if you have never used it as well. I cut myself short, but you will fall into a trap. So I just mentioned that. if the subscription API runs on 8080, test containers will actually map the port to something else. It will not run on 8080. It will find a random port which is available and give you this random port. The reason for that is most of the time it runs on CI and it just doesn't want that it crashes with anything. Now our CI wouldn't have the issue because it runs in Docker itself, but a lot of CI systems still run not isolated. So test container will never expose it to the ports you give it, but it will map it to something and you will have to deal with the mapping. So therefore I return this mapping of the different ports, and then the other codes will get this. Okay, that was the test container run. Event registry is not important. Finally, it is important, but it's too detailed now. I create the topics, I start the worker, and I will have ingested some of the Kafka ports here. They're inside here. I start 3 workers on these ports. Finally, I kick off there, and this group of commands will always publish. So we publish here pops 3000 with this market, and this will happen again and again. Here a couple of first tests. So here I just test if I have, from the test container, I got some ports back. Here I just see if these topics are defined in the event registry, nothing exciting, but this is actually more exciting already. This says in, whatever this means in tested from Metosim, this means this part, the right-hand part needs to be in the left-hand part, but this means eventually the right-hand part needs to be in the left-hand part, because it takes a while. We are in a distributed async world. It takes a while until the workers are really available, and they have initially only 0 tasks. Therefore, eventually, what does it mean tested? We'll do it again and again. How long is defined here in the beginning. It does it 1 minute. It's pretty slow, yeah, because the rebalance is sometimes slow, and it does it every 500 seconds. So now let's not go through all of them. Maybe we stopped here. So here we publish 6 subscriptions. We publish here Marta with somewhere an invalid key. So I just map this. And then we check that we have published here for these endpoints. And let me find the next. Eventually, this is here. Eventually, the number of the subscription needs to be 6. This will be a query against the subscription API. Now we ask the worker here if it has 8 tasks. We have 6 subscription, but one of them, the assets, has 3 tasks, and therefore 8. So I personally find it quite readable, the whole stuff. So therefore I like this. Let us skip something here. What is this? Here we check the task distribution. And here I check the offsets. That means eventually I should have the lag should be 0. That means the task has actually read all the stuff, and the numbers indicate how much data I have read, and poor Marta hasn't read anything. Okay, this is more or less this all. Maybe it's too detailed by now, but let's have a look what it has done. Oops, okay, need to go up again. And we went through this. So I think this was a lot of talk by now. Of course, I plan to show you much more, but it is now more than the 40 minutes. So I thought it's now a good time to stop. What do you think, Bruno?